Imagine a place where a satellite can circle the Earth in 90 minutes. Where a tourist on vacation wakes up and takes in their view from a hotel room in space. Or where a speck of paint becomes a lethal weapon, able to blow a hole in the side of a spacecraft. These are the realities of Earth orbit, the gateway to the solar system. And it's the turf of astronauts, space junk, and the ultimate thrill seeker. Journey out with us to the edge of space. In the not-so-distant future, a human will board a rocket, sit on an open platform, and launch 120 miles straight up into Earth orbit. Dressed in a high-tech spacesuit, he'll peer through a quartz-coated visor and take in an unparalleled view.
Being in low Earth orbit is spectacular. When you look up, you see the inky blackness of outer space and the stars shining even in daytime. Looking down, you see the hazy blue glow of this gigantic ocean right underneath your feet.
This observer is a space diver, a new breed of ultimate thrill junkie. And as he unhooks from his safety harness and stands at the edge of space, he takes one last look out to the universe and leaps, speeding towards Earth below. Space diving is one of many futuristic ideas planned for Earth orbit. The zone of space that surrounds Earth and begins 120 miles above sea level. It's the home to satellites and the space station. And if orbital outfitters have their way, the ultimate extreme sport, skydiving from space. Earth orbit is a window to the universe, and perhaps will become an extension of Earth itself for industry, exploration, and fun. But the environment in Earth orbit is very different from home. Oxygen ceases to exist here, and the atmosphere that provides a protective shield around Earth disappears. Cosmic threats lurk for those who dare explore here.
We forget that outer space is dangerous. We forget that in outer space we have cosmic radiation, we have solar flares, we have meteors, we have space debris. It's an obstacle course being out there in outer space.
Like free-fall skydiving junkies who leap out of planes and speed towards Earth, space diving might seem like the ultimate thrill. But its idea is based on very serious intentions. Dr. Jonathan Clark, a Navy flight surgeon and former Navy high-altitude parachutist, is one person behind the space diver concept, but for very personal reasons.
I wasn't assigned to NASA to work on space operations. And then my wife was an astronaut.
Columbia, Houston, UHF comm check.
She died on the Columbia mission in 2003.
While military pilots routinely eject safely from imperiled aircraft, currently, there is no evacuation procedure for astronauts to eject from a spacecraft during a catastrophic event.
About 1% of the time, we have a major booster rocket failure or a catastrophe in outer space.
Perhaps the skydiver spacesuit will become a new safety device for astronauts to use on missions. And its first test is a 160,000-foot jump. To survive re-entry, the skydiver spacesuit has many critical features. a protective one-piece jumpsuit that insulates from the negative 40-degree Fahrenheit space environment to the 464-degree heat generated from re-entry. Small gas jets on each glove to orient and direct the body during weightlessness. A full closed-loop oxygen system that will recirculate and remove carbon dioxide for the 10-minute trip home. A drogue parachute to stabilize the space diver as they come closer to Earth. And a traditional parachute that will deploy at 3,000 feet for a safe landing. And the journey will be spectacular. In the first 2 minutes of the jump, the space diver will reach speeds of 2,500 miles per hour while in free fall. Atmospheric drag will heat the spacesuit to 474 degrees Fahrenheit and slow the space diver to terminal velocity, 120 miles per hour. As his drogue parachute breaks free at 7 minutes, he will begin to slow down. Finally, at 3,000 feet, a regular parachute deploys, and the space diver lands safely on the ground.
It will be cinematic.
Chris Gillum is a Hollywood costume designer and chief designer for Orbital Outfitters. He has an array of spacesuits he's designing for the company. His passion for accuracy in his costumes eventually landed him a real commission with NASA to design a woman's upper torso spacesuit.
While looking at real suits very close up, you start to understand that they're not just a white jumpsuit with plastic fittings and a bubble helmet. Think of a spacesuit as a personal spacecraft.
To protect the body, spacesuits are designed in layers.
Imagine the kind of clothes that you'd have to wear if you were walking through the Sahara on twice its worst day ever, and then make one more step and you're into the Arctic. That's the kind of clothes you have to wear.
And when considering the form and function of his Orbital Outfitter suits, Gillum looks back in time to medieval armor to help create future designs.
Here is our 14th century hourglass gauntlet. That knuckle bow is almost identical to the one that is under the fabric cover in a shuttle spacesuit glove. And interesting enough, it's almost the exact same shape as well. And it performs the same function.
While space diving might be years away from becoming a reality, thrill seekers are already making their way to the edge of space, the realm of Earth orbit. Up until 2001, the privilege of orbiting Earth was reserved for the elite few. Astronauts chosen to work in space. But that's before space tourism became a reality.
One of the dreams of most of the people associated with the spaceflight world is to actually fly themselves. And so space tourism has been an important component in people's thinking about spaceflight from the very beginning.
Right now, Space Adventures Limited is the only company delivering that dream.
We are the world's only private space travel company.
Space Adventures started 10 years ago when its first client took a very high-altitude ride on a Russian jet.
When he came back and talked about what it was like to see the curve of the Earth and the black sky above, I knew that we would have a great business and there would be literally millions of people out there in the world who wanted to participate in Space Adventures experiences.
Then, in 2001, American investment manager and multimillionaire Dennis Tito approached Space Adventures about arranging a trip into Earth orbit, and the era of private space tourism was born.
The flight of Dennis Tito to the International Space Station was an enormously significant accomplishment, and many people watching in the space community cheered. They thought this was great. It's a new age that has begun.
I love space.
Space Adventures Limited now offers trips to the International Space Station for $33 million.
You'll learn about the rocket. You'll learn about the spaceship that you're going to fly in. You'll learn about the space station. You'll learn about what it's like to live and eat and work and even go to the bathroom in space.
To get to the space station, space tourists must hitch a ride with the Russians in a Soyuz capsule.
It's flown successfully for 35 years. This great feat of human engineering will deliver you from the ground to orbit in less than 8 minutes.
Once delivered to the space station, space tourists live like real astronauts.
Comfortable is a relative term. So if you're comfortable on a camping trip, then you'll be fine on the space station. And if you're at all used to being in the outdoors where you don't have all the comforts of home, then you'll be quite comfortable living in a spaceship.
The food is great, but you're not going there for the food. The real enjoyment of space is being able to float weightless and see the Earth and be really part of the future of space exploration. And being able to see what it's like to step off the planet and go somewhere that very few people have been before. You'll be seeing the Earth in all its glory and splendor. You'll be watching 16 sunsets and sunrises every day because you travel so fast around the Earth.
Right now, taking a trip to space is too expensive for most private citizens.
If you were to just go in low Earth orbit around the Earth, that would cost about $10,000 a pound. That's your weight in gold.
There are many companies currently designing new spacecraft to make space travel affordable.
I can't tell you when it will be $4,000, but I can tell you it'll never be $4,000 if it doesn't start off at $40 million.
Regardless, Space Adventures Limited has big plans to expand their offerings in space.
One of our future clients will be undertaking a spacewalk for the first time. Additionally, we're very excited about our circumlunar flight program and doing a flight around the moon. They will come literally within 100 kilometers of the lunar surface.
Sending private citizens into space has changed the paradigm for space exploration.
We've really, I'd say, banged down the door for the rest of the industry. There are many people now who are interested in opening up this frontier and doing it privately, and we hope to be seen in history as the catalyst which really motivated that entire industry to begin.
Perhaps the most exhilarating part of a space adventure is getting to the edge of space. But space is a big domain, and there are threats here that are unlike anything we have on Earth. Earth orbit, our edge of space, is generally divided into 3 parts. Low Earth orbit is an 1,100-mile wide belt that is closest to Earth's atmosphere and begins only 120 miles above sea level.
There are tremendous advantages to low Earth orbits. First of all, most of the manned space program takes place in that radius.
Start 1, 0, and liftoff of Space Shuttle Endeavour.
Also, spy satellites, communication satellites, weather satellites occupy that low Earth orbit.
Low Earth orbit is like a busy city, lots of activity. The Hubble Space Telescope and the International Space Station call low Earth orbit home. Soyuz and the Space Shuttle complete missions here. Objects and people in low Earth orbit can travel around Earth in an astounding 90 minutes.
45 minutes on the sunny side of Earth, 45 minutes on the dark side of Earth.
Houston, you're go for landing, over.
Except for a few trips to the moon, all of humankind's visits to space have been to low Earth orbit.
The bottom line in low Earth orbit is if you can't reach it, you can't go anywhere else. And human spaceflight ultimately is about going somewhere else. Low Earth orbit is kind of the entry point for that effort.
Above low Earth orbit is a region called medium Earth orbit. This wide stretch of space is 1,200 to 14,000 miles above Earth. Many communication satellites are launched into orbit here, including global positioning satellites.
GPS satellites roughly orbit the Earth at about 12,000 miles, what we call a semi-synchronous orbit. So basically, they orbit the Earth twice per day, once every 12 hours. GPS is set up into 6 orbital planes. So if you can imagine a globe, there are 6 orbits positioned in equal spacing around the Earth, with roughly 4 or 5 satellites per orbital plane. And basically that gives us coverage around the world.
GPS satellites sit at this altitude so that multiple satellites are in view from one location on Earth at any time of day.
It takes 4 satellites to get you your exact location. The first will give you a roundabout area, the second will refine it, as well as the third, and finally the fourth says you are exactly here.
Medium Earth orbit is also home to the treacherous Van Allen radiation belts. These belts of high-energy charged particles can send a $300 million satellite spiraling out of control, or give a human being a fatal dose of radiation. These belts stretch out from Earth like elongated rings. Satellites are carefully placed in specific altitudes to avoid these destructive belts of particles from the Sun. Even farther out lies high Earth orbit, or geosynchronous orbit. If low Earth orbit is a busy city, high Earth orbit is rural farmland. 22,000 to 35,000 miles above sea level, satellites hover above Earth, taking in an unparalleled view from a distant vantage point. Here, over 2,000 satellites call high Earth orbit home.
These satellites appear to be stationary. They make a circuit around the Earth every 24 hours, but so do we. So we have the optical illusion that these satellites are sitting there in outer space.
But in order to reach Earth orbit, an object must first leave the ground and be delivered into space. To do this, a rocket or spacecraft needs to achieve the appropriate speed and hit a target direction and altitude. Go even a few miles per hour too slow, and the forces of gravity and drag of the atmosphere will pull a spacecraft down, crashing it to the ground.
So the idea is to get out of the drag of the lower atmosphere, beyond all that turbulence and friction, and then start racing for the right direction and speed after you get up above the sensible atmosphere.
And there's a very good reason why spacecraft launch straight up rather than at an angle like an airplane.
So what typical space launches do is go straight up through the atmosphere to get through the thickest part initially, and then they begin to arc over a few miles up and then start to increase their velocity in the desired direction.
To reach a target orbit, a spacecraft must travel 17,500 miles per hour and follow a specific trajectory from the ground to desired altitude. Even 1 degree off, and a spacecraft will end up in the wrong orbit. After an 8-minute ride and millions of gallons of fuel burned, a spacecraft is now in orbit. An orbit is a reoccurring path around another object. Like Earth revolving around the Sun, a satellite or spacecraft is held in orbit by gravity. Earth's mass creates a gravitational force that deflects an object's path from a straight line. It might be assumed that Earth's gravitational pull loses much of its influence this high in the sky. But in low Earth orbit, Earth's gravity is only 2% less powerful than it is on the surface of the planet.
The way you stay in orbit is to go at a high enough speed or velocity that you are falling back to the Earth, but you're going so fast that your curved path actually never strikes the curved surface of the Earth. You just keep falling around the world over and over again. So you're not leaving the gravity behind, but you're being spun around the planet by gravity. It's what's holding you in this circular path around the planet. and it's making you fall back to Earth.
In theory, objects can stay in orbit forever, as long as they have enough speed to resist the pull of Earth's gravity. There are two types of orbits, circular and elliptical. Circular orbits are for satellites or spacecraft that need to maintain a consistent altitude and travel in a regular circle around Earth. Mapping satellites, GPS, and weather satellites all use circular orbits. Elliptical orbits are oval in shape. They're used when a high altitude is needed for part of the orbit, without having to go all the way to high-altitude circular orbit. Spacecraft delivering satellites into high orbits use elliptical orbits to deliver their payloads. Whether traveling in a circle or an elliptical path, there are many things in Earth orbit that are dangerous. In October 2007, the U.S. Navy shot down an out-of-service satellite with a cruise missile before it re-entered the atmosphere. The reason? The satellite carried hazardous material on board, and had it crashed to the ground, could have poisoned thousands.
That hazardous material was 1,000 pounds of hydrazine, which is a standard propellant.
The operation was called Burnt Frost, and it was the most elaborate effort thus far to protect the world from a serious yet growing problem called space debris, or space junk.
Space junk is anything that's man-made that was put into space and is no longer functioning. Oh, we've got junk that's been up there for as long as we've been in space.
Like a junkyard slowly becoming cluttered with debris. From the first launch of Sputnik in 1957, debris has steadily been accumulating around planet Earth.
50 years into the space race, we have littered the heavens with our garbage.
And now, about 20,000 pieces later, Earth orbit has turned into a deadly debris-filled junkyard.
It looks like the Earth surrounded by a hive of bees.
Most of the space debris includes shards of rockets, satellites that no longer function, or pieces of an object that have broken up after a launch. Caught in Earth's gravitational pull, these pieces are traveling upwards of 22,000 miles per hour.
Say more than 10 times faster than a bullet.
A collision between functioning objects such as satellites or inhabited spacecraft and space junk could be catastrophic. The Joint Space Operations Center, or JSPOC, is a top-secret Air Force surveillance unit that makes it their business to track every object that orbits around Earth, including space debris.
We use a number of different sensors around the world, known as the Space Surveillance Network. It's a network of 29 stations all around the globe, radars as well as optical telescopes that track over 18,000 man-made objects in space. And that includes active satellites as well as dead satellites, and then rocket bodies that were associated with those launches, as well as debris, things that have just shed off. If they were to run into each other, it really would be a catastrophic conjunction.
To be tracked by JSPOC, debris must be at least 2 inches wide. There are much smaller objects that cannot be tracked.
On most of my shuttle flights, we always saw small pits in the windows about the size of a pencil point.
The highest population of debris are in low Earth orbit.
And in 2008, an intentional collision between 2 satellites created an international outrage and a cloud of debris that threatened low Earth orbit like never before. Our edge of space is Earth orbit, a new frontier for space tourism and exploration. But danger lurks here, space debris, and it threatens our spacecraft and satellites like never before. In 2007, the total estimated amount of space debris was 20,000 pieces, 14,000 of which were trackable. Then, in 2008, China's space program intentionally crashed 2 satellites together as an anti-satellite test. The international space community was outraged.
The 10th of January of 2007, the number of objects we were tracking was less than 14,000. Here we are 16 months later, and we've increased that number by over 30% to over 18,000.
The problem of space debris continues to grow, and collisions have already occurred between space junk and functioning objects.
One of them was a piece of debris that struck a gravitation boom on a spacecraft, severed the boom.
To avoid future collisions, JSPOC is in constant contact with NASA and other international space entities to inform them when a spacecraft or satellite might be threatened, so that the spacecraft could be maneuvered around the space debris. Much like a boat maneuvers around hazards in a waterway.
Beneath the surface of the water here, what you can't see is what's going to actually give you the most damage if we run into a log or a snag beneath the surface. And in orbit, that's the same problem that we face. We don't track all the debris that could actually cripple or kill your spacecraft. And we rely on the fact that you're just statistically unlikely to hit a piece of debris to protect you. And that insurance policy is going to run out someday.
Fortunately, there haven't been any catastrophic collisions between inhabited spacecraft and space debris, yet.
We've never seen a human-piloted spacecraft run into orbital debris and been damaged, but we've had some close calls.
Objects, no matter what their size, are always in danger of being pulled out of their orbits by orbital decay. Orbital decay occurs when an object loses speed caused by friction and begins to be pulled towards Earth by gravity. Atmospheric drag is the major cause of orbital decay, like a bicyclist on the road.
When you're pedaling along at a constant speed, you're balancing your muscle power against the drag on the tires from the road and the resistance of the air that you're moving through. And you overcome that resistance on the bicycle with your muscles, or in space by firing your rocket engines to add a little speed, overcome that air resistance. That's what has to happen in space to keep the space station from falling back to Earth and burning up. And if you stop adding thrust, that air resistance will eventually slow you down to the point where you'll stop or fall back into the atmosphere and re-enter.
Some pieces survive re-entry. And the size of these pieces that have fallen to Earth is terrifying. In the last 40 years, 17,000 pieces of space debris have survived re-entry.
Back in 1997, we had a 570-pound stainless steel tank that landed about 50 yards from our farmer's house in Texas. He was not particularly pleased by that.
If a piece of debris does survive re-entry, it travels at subsonic speeds of 120 miles per hour until it hits the ground.
There was a re-entry that came in to Cape Town in South Africa. It was during the day. There were people out working in fields. They heard a sonic boom, and they looked up, and they basically saw this material coming down.
The Aerospace Corporation in El Segundo, California, is a facility that collects and studies space junk for the military and private companies.
This is a piece of what was once a piece of space junk. This was a part of a rocket stage that was used to put a GPS satellite in orbit. And here you can see the brackets that were actually melted off as this came down. We actually have cut samples here to try to understand what happened in this area, how hot did it get, and we use that information to improve our models.
Understanding how these pieces survive re-entry is important for future spacecraft and satellite construction. Recovering and reusing critical spacecraft parts could save millions in manufacturing costs. However, collecting space debris remains tricky.
3/4 of the Earth's surface is water, so a lot of it lands in the water. So when you find a piece on the ground, it's actually a very rare event.
It's estimated the amount of space debris will double by 2050. But that hasn't deterred entrepreneurs who continue to explore Earth orbit as a business location. For a mere $2,500, Memorial Space Flights, which began service in 2008, will launch ashes of a loved one into low Earth orbit. It's a fitting end to anyone who dreamed of one day visiting outer space. This is just one of the many ideas entrepreneurs are developing for Earth orbit. But to run a business in space, there needs to be a way to obtain permanent occupancy.
Here we are in the early years of the 21st century, and I foresee space becoming an industrial park.
Skylab, Mir, and now the International Space Station have all provided an arena for long-term habitation and experiments in space. What if private companies could also have spacecraft orbiting the Earth?
I think we were and are the first company to have deployed that kind of structure.
Just off the Las Vegas Strip, Bob Bigelow and his team at Bigelow Aerospace are hunkered down in a high-security facility creating a new generation of spacecraft.
I'm living out a childhood fantasy is what it is. And I think that we are involved in something really important.
Private industry is exploring the opportunities of our edge of space. Bigelow Aerospace is developing inflating workspaces called Genesis to launch into Earth orbit. The technology was inspired by NASA.
I came across an article about a technology that NASA had been working on, and I thought, oh my God, this is great.
NASA developed an inflatable module, a room called the Transhab, that was going to be joined to the space station to provide more living space. NASA was never able to afford executing that plan.
Eventually, after a number of years, we acquired the licenses from NASA for their patents.
The concept is ingenious. Bigelow spacecraft are inflatable pods that tuck into the nose of an unmanned rocket during launch, then expand to 3 times their travel size to full capacity once released into orbit.
In a rocket fairing, you only have so much volume, so much room. Like this bottle. That's as big as it gets, that's it. But if you launch something in that volume that can later expand to 3 times its size, you have a lot more room to do something with.
We use compressed gas to expand it into its form.
The inflatable spacecraft can be adapted to whatever a client might need. Research laboratory, manufacturing facility, hotel space, all emerging industries for Earth orbit.
We can host a variety of different kinds of clients, and they only have to pay for the specific time that they're interested in.
The spacecraft is assembled from very durable but bendable materials called soft goods systems.
You've driven all your life on soft goods. You've driven on tires. The inflatable systems can be extremely reliable and very strong.
Bigelow's not worried about the reliability of his launch system. The Dnepr-18 rockets he's using are the same ones the Russians trust with some of their most precious payloads.
They have about 1,100 of those rockets with nuclear missiles on them right now. We're not going to fail because the rocket failed.
Once in orbit, instrumentation is powered by 4 solar panels, just like the International Space Station. The Genesis spacecraft is a new generation of space station, and it might be a vast improvement from the government-issue brand.
What we're working on, if we're successful, is a much safer vessel for humans to be in than the aluminum cans are.
Our inflatable hull structure is adequate to protect against any type of thermal effects, micrometeoroid protection, radiation effects.
Bigelow Aerospace now has 2 private spacecraft, Genesis 1 and 2, orbiting 340 miles above Earth. The only privately owned spacecraft of their kind orbiting in the edge of space. Launching spacecraft into Earth orbit is only one challenge. Picking an appropriate inclination for its orbits is another.
The orientation of an orbit really is just a measure of the degree of tilt from the line running through the equator. You can have anything from 0-degree inclination to 90-degree inclination. The 0-degree inclination is absolutely no tilt whatsoever from the equator, and that is called an equatorial orbit. Whereas if you have a 90-degree tilt from the equator, that is the polar orbit.
Satellites and spacecraft are launched into different inclinations depending on their mission, because different inclinations pass over different parts of Earth.
If you're going around the Earth, around the equator, what do you get to see? It's just what's below you, which is going to be what? The equator. So an inclination of the orbit at, say, 56 degrees covers almost all of the population of the Earth.
A polar orbit satellite has the ability to view the entire Earth in a few orbital rotations. As the Earth slowly rotates below, the satellite keeps sweeping overhead, allowing the entire Earth to be observed in a short period of time. If the mission is for espionage or observation, sun-synchronous orbits allow satellites to pass over the same point on Earth at the same time every day. They shift 1 degree each Earth day to stay in sync with the sun at a given location. If constant communication is necessary, geosynchronous satellites are positioned far away from Earth so that entire continents are within their view.
It matches the rotation of the Earth and appears to hover in the sky. It's a very useful trait of that orbit, because you can then stay constantly in radio or television touch with the spot on the ground below.
Earth orbit is the natural extension of Earth's occupation in space. And if future plans pan out, the industrialization of the edge of space will happen in the near future. It was only 40 years ago John Glenn entered Earth orbit. What the next 50 or 100 years holds for the future of Earth orbit is as exciting as perhaps a walk on the moon once was to an older generation. Bigelow Aerospace has already reached a major milestone by launching their Genesis 1 and 2 pods into orbit. But future spacecraft will be ready for private citizens.
Nobody's done this before. I mean, people have gone to space, but what we're trying to do is make it available.
It's called Sundancer, a 300 cubic meter inhabitable space that will have the capacity to support up to 3 human lives indefinitely.
We have to add a lot of life support equipment to make sure that the environment is sustainable for a crew of 3. That goes into anything from the air concentration system, where oxygen has to be delivered, CO2 has to get removed, all the way through more rigorous thermal control and humidity control.
One Sundancer spacecraft offers more space than is currently available on the entire International Space Station. Eventually, multiple pods will be connected together, like Tinker Toys, for larger facilities.
What kind of shape you're choosing depends on the purpose, the mission for the spacecraft.
But like pioneers setting off across the open sea in search of new land, this is uncharted territory.
We have an opportunity to turn that vision into a reality. And so far, that's exactly what we're doing.
They are one group of many that dream of permanent occupancy at the edge of space. One thing remains clear. Earth needs an easy way to deliver spacecraft, cargo, and people into space to take advantage of Earth orbit. And the ideas are spectacular.
There have been all kinds of concepts, like space elevators.
How about a space fountain? A highly energized wave of particles that lifts cargo up into Earth orbit.
The key is finding a cheap way to get those materials up to space.
Or perhaps the resources of space can be mined in a facility orbiting Earth.
Using the resources that are on the moon and the asteroids nearby to build things in space themselves, not have to spend the money to haul them up from the ground. For example, Lewis and Clark, when they went across the continental US, they didn't haul all their drinking water and firewood with them from St. Louis on the way west. They used what they found along the way.
Earth orbit's greatest gift might be sustainable power. Imagine an array of solar panels that generates enough power to light up a continent.
That's probably one of the most promising avenues to pursue in the next 50 years in space, is to find a way to make cheap solar collectors and then build the collecting antennas on the ground so that we can use inexhaustible solar power to reduce our reliance on the finite supplies of fuel and energy we have here on Earth.
In 1994, more than 20 pieces of the Shoemaker-Levy 9 comet pummeled Jupiter.
There were big black scars all across the face of Jupiter, so large even that they could be seen clearly even with amateur telescopes.
The largest comet fragment was more than a mile wide, and the force of its impact was equal to 6 million megatons of TNT.
That's about 100 times or more of the entire nuclear arsenal of the world. So if you took every bomb in every corner on Earth and exploded it in one big explosion, you wouldn't even begin to touch the power of this fragment colliding into Jupiter.
But guess what? Even that type of power isn't enough to qualify as one of the biggest blasts in the universe. The first event to make the top 10 was many times more devastating. Number 10, death from the sky. The smallest blast on our list may still have been big enough to wipe out the dinosaurs by blocking out the sun with smoke and debris. It's the Chicxulub impact, the asteroid that crashed into Mexico's Yucatan Peninsula about 65 million years ago. A 6-mile wide space rock, taller than Mount Everest and almost as wide, thundered into Earth.
So I'm sitting in front of the meteor crater in Arizona, and this is about 3/4 of a mile wide. So if we were to drive across this at about 55 or 60 miles per hour, it would take like a minute. Well, the crater created by the asteroid that impacted the Yucatan Peninsula, it would take over 2 hours to drive it at about the same speed. So you can imagine how much larger that crater is than this one behind me.
The 112-mile diameter crater is big enough to fit New York City, Philadelphia, and everything in between inside. If it struck today, about 12 million people would be killed instantly, not to mention the damage and casualties that would spread beyond the crater. That's because the energy in every blast is released in several ways, such as light during the blinding flash of the impact, and heat, capable of spreading wildfires across much of the globe. But with collisions, most of the devastation comes from the energy of motion, known as kinetic energy, which creates the crater and the flying debris.
The energy in the impact that created the crater at Chicxulub had to have been enormous, probably about 250 million megatons. That's a lot of energy. The largest bomb ever exploded on Earth was 50 megatons. So that compared to 250 million gives you a sense.
It was also about 40 times greater than the energy released by the largest Shoemaker-Levy 9 comet fragment to hit Jupiter. And figuring out the kinetic energy released in a huge asteroid impact is all a matter of plugging some very big numbers into a simple equation.
The key thing to keep in mind when considering the energy in these kinds of collisions is that the formula for what's called the kinetic energy, the energy of motion, is 1/2 mv squared. The mass and then the square of the velocities.
Mass is the weight of the object, and velocity is the speed it's traveling.
You can have a huge amount of energy for a massive enough or fast enough object.
Considering that the Chicxulub asteroid weighed nearly as much as Mount Everest and was moving at over 50,000 miles an hour, about 50 times faster than a bullet from a revolver, it's no wonder it was one of the biggest blasts in the universe. But what about its effect on the structure of the entire planet? An explosives expert places a small charge just under the skin of a watermelon to simulate the type of energy released when this asteroid slammed into Earth.
As you can see, something that would be devastating to us is not too devastating to the planet as a whole.
So there's still plenty of room for the blasts to get bigger. Number 9, Martian impact. Luckily, Mars, and not Earth, was the target of an asteroid 200 times larger than the one that slammed into the Yucatan Peninsula.
The asteroid that impacted Mars about 3.9 billion years ago was 1,200 miles wide. Now, that's about the size of Pluto. And if you imagine most of the continental US, from Denver to the Florida Panhandle and Chicago down to the south of Texas, huge.
And that's just the size of the asteroid. The crater, known as the Borealis Basin, is another story. The hole covers about 40% of the planet.
So the Borealis Basin on Mars is about 5,300 miles wide. Now the crater behind me is not even a mile wide. So you can imagine multiplying this by over 5,000 times, and that's the size of the impact crater on Mars. That's about the size of the continent of Africa. Amazingly huge.
While the speed of the asteroid that smacked Mars wasn't much different than the one that hit the Yucatan Peninsula, the mass was many times greater, leading to a much larger release of energy.
Probably about 1,000,000 times more energetic. So it would be about 250 million megatons of energy, and that's a lot of energy. And that's why you got such a big basin.
Something like that hitting Earth today would put the instant death toll in the billions and would probably wipe out all life on the planet soon after. But the next blast did blow an even bigger chunk of crust off our planet, luckily before life even existed here. Number 8. The Big Splat. Instead of Mars being a target, imagine an asteroid the size of Mars slamming into Earth. Most planetary scientists believe that's exactly what happened soon after the Earth formed about 4.6 billion years ago. It's known as the giant impactor theory, also nicknamed the Big Splat.
The early solar system was a much busier place than it is today. Basically, it hadn't settled down yet. So there are lots of fragments running around, producing all sorts of collisions, which ultimately produced the bodies we know today.
Earth was still a molten wasteland, devoid of life back then, which is a good thing, since the force of that collision would have ended life in its tracks. So how did the planet recover from the most violent event in its history? Many of the biggest blasts in the universe are caused by comets and asteroids slamming into planets. These impacts can unleash hundreds of times more energy than the entire nuclear arsenal on Earth. But number 8 on our list is even more powerful than that. A blast caused by a rock the size of a planet slamming into Earth. It actually happened soon after the Earth had formed, about 4.6 billion years ago, when an object the size of Mars, sometimes known as Theia, slammed into our world with catastrophic effects. Compared to the Pluto-sized asteroid that smashed into Mars, the Mars-sized rock that nailed Earth was more than 3 times larger, releasing much more kinetic energy.
The Theia impactor that knocked off the crust of Earth was probably about 10 times more powerful than the Borealis Basin impactor.
But this incredibly destructive force also had some very important benefits.
So when Theia impacted the Earth, it happened probably at a glancing blow. And in doing so, the iron cores of the 2 planets actually melded together and formed a larger iron core and a larger Earth. Now, Theia's mantle probably got completely blown off in this impact because it's a little smaller than Earth, and some of the Earth's mantle got blown off. So you have all this mantle debris floating around, orbiting, and it actually coalesced to form the Moon.
The Moon stabilized Earth's axis, preventing it from tilting wildly, which keeps Earth's climate steady. It also slowed Earth's rotation over time to the 24-hour days we have now. Once again, to simulate the power of this blast, an explosives expert places a charge on a melon representing Earth. Could this be the one that blows the melon away?
even though there's a lot of damage, the basic structure is still intact.
With the heat of the impact, the Earth and the debris were both molten. And that molten state is the reason why the impact didn't leave a massive crater behind. The molten Earth reformed as a sphere and eventually cooled. So is there any kind of impact that can turn a planet into dust? Number 7, when worlds collide. Deep in space, two planets, one the size of Venus, the other Earth, are on a collision course. They're rocky planets, possibly even harboring life. Something in their solar system has pulled them out of their regular orbits, and instead of a glancing blow, they smash together in a head-on collision. Anyone standing on those planets would have witnessed a terrifying event.
You can imagine if you had a direct view of the planet moving toward us. That means the sky would quickly fill completely with this planet about to impact, and then it would be over like that. It would be such a rapid extinction of life that you probably wouldn't have time to think about it.
This isn't some fictional doomsday scenario. Some researchers think this massive blast rocked the cosmos within the last 1,000 years. In a binary star system about 300 light-years away. It's known as BD plus 2307 in the constellation Aries.
It has a tremendous amount of dust in it. 1 million times more dust than in our solar system. We think that this dust may have been produced by the collision of two planets, roughly the size of the Earth and Venus, just head-on, whack. Shattering each other, producing a tremendous amount of dust.
It takes enormous amounts of energy for two planets to pulverize each other into dust. Now, instead of hundreds of times the world's nuclear arsenal, we're talking millions of times or even billions of times that energy. With this even larger charge, we're not just going to break off a chunk of this melon, we're going to blow it to smithereens.
But as terrifying and destructive as planetary collisions can be, they're still much smaller than the different types of blasts that come from stars.
It's a whole new ballgame. The main reason is that there's a lot more mass in a star than any planet-sized object. And then there are all kinds of mechanisms that can take place involving nuclear fusion or various processes that involve gravitational collapse, which can drive a lot of energy as well.
One of these energetic blasts is number 6 on our list, magnetar flares. Magnetars are rapidly spinning neutron stars, which form when stars several times larger than our sun begin to die and collapse in upon themselves. Imagine if our 865,000-mile-wide sun suddenly compacted to the 12-mile length of the island of Manhattan. All of that matter is condensed into something so dense, it's estimated to be 10 billion times stronger than steel.
To give you an idea of how incredibly dense neutron star material is, if this cap was filled with neutron star stuff, it would weigh 100 billion tons on Earth. More than this hill, as much as an entire mountain.
The magnetar name comes from the fact that certain neutron stars, for reasons that are still unknown, have the strongest magnetic fields in the universe.
The magnetic field of a magnetar is exceptionally strong. It can be 1,000 trillion times as strong as Earth's magnetic field. That's fantastic.
The magnetic fields are so intense that if a magnetar suddenly appeared halfway between the Earth and the Moon, it would be strong enough to disrupt all of the electronic equipment on the planet, including stripping the information off every credit card on Earth. And the reason magnetar flares are so powerful is that the magnetic fields around certain areas of the star sometimes twist themselves so much that they can't twist anymore, and suddenly release like a spring.
The process is similar to a solar flare in that it's the magnetic field that's giving rise to the energy. It's the shaking and tangling and sometimes the reconnection of lines of force going in different directions that gives the energy that powers the flare.
But unlike planetary collisions, where kinetic energy dominates, magnetar flares shoot out most of their energy as electromagnetic radiation. In other words, light. And one magnetar flare in particular was strong enough to blind satellites orbiting Earth from 50,000 light years away. The biggest blasts in the universe dwarf anything we can imagine on Earth. We're already billions of times beyond the entire nuclear arsenal of the world. Number 6 on our countdown are the flares that burst from incredibly magnetized neutron stars, known as magnetars. And one of the most powerful ever observed from Earth released as much energy in just over 1/10 of a second as our sun does in about 100,000 years. The blast in 2004 came from a magnetar known as SGR 1806-20 in the constellation Sagittarius. It's about 50,000 light years away from Earth on the far side of the Milky Way.
It was incredibly powerful. All that energy came in 1/10 of a second. It blasted the detectors and satellites that happened to be flying around up there. In fact, it was the brightest blast ever seen from an object outside our solar system. And yet, it was 50,000 light years away.
But what does brightness have to do with the power of a blast?
So I'm standing in a dark room here, and now I'm going to turn on a light bulb. How bright that light bulb appears to me depends on 2 factors. It depends on how intrinsically powerful or luminous the light bulb is, its wattage, how much energy it puts out per second, and it also depends on the distance of the light bulb from me. When I'm close to the light bulb, I see that the light bulb is bright. If I move a factor of 2 farther away, then in fact it looks a factor of 4 fainter. That's the inverse square law of light. The power of the light bulb has remained the same, but by being twice as far away, I get only 1/4 of the light reaching my face and my eyes. Astronomers measure the apparent brightness of the star or the explosion. They figure out its distance through some other technique, and from those 2 variables, they figure out the power or the luminosity of the source.
That light is released not just in visible wavelengths, but across the electromagnetic spectrum. And anytime researchers detect gamma rays, like they do in magnetar flares, they know it must be a big blast.
Gamma rays are a type of light, but a much more energetic light than we see with our eyes. So the spectrum of light that we're familiar with goes from very low energy and through the visible part of the spectrum, the light that we see, all the way out through X-rays into this extremely high energy component of light, which is called gamma rays.
Even a 1/10 of a second short gamma ray flare, like SGR 1806-20, would still be able to fry the Earth with radiation from many light years away. as long as the full force of the flare was aimed at Earth. But not all of the biggest blasts in the universe are over in a fraction of a second. Number 5, the 100-million-year blast. 2.6 billion light years away from Earth, a supermassive black hole, billions of times the mass of our Sun, has been wreaking havoc in the center of a cluster of galaxies. Known as MSA 735, it's been shooting out 2 continuous jets of particles in opposite directions. Scientists believe the jets have been raging for the past 100 million years, punching 2 huge bubbles into the surrounding galaxies.
MSO 735 really is the prototypical example of a black hole blowing bubbles. What we're seeing here is giant cavities being evacuated by these powerful jets. They transport vast sums of energy down from the black hole out to huge distances, maybe about 1 million light years or so.
1 million light years is 10 times wider than our Milky Way galaxy, which means these jets are powerful enough to create 2 very big bubbles.
The total energy within these 2 bubbles is stupendous, far exceeding any other amount of concentrated energy that we know of in the universe. However, it must be remembered that the energy was released over 100 million years. That means that per unit of time, the total amount of energy released wasn't all that big.
Still, the jets are strong enough to shoot the particles out at millions of miles an hour, about 1/4 of the speed of light. The jets and resulting bubbles only come from about 1% of the most massive black holes in the universe. That's because the forces near these monsters are so huge that instead of swallowing everything, they actually end up pushing some particles away.
It's important to emphasize that these giant explosions are not the explosion of the black hole itself, but rather an ejection of particles from near the black hole, the vicinity of the black hole. By colliding with one another, they can, in some cases, be ejected out of the vicinity of the black hole.
But how can this 2-sided blast possibly keep going for 100 million years? It's all a matter of how much cosmic stuff is available, as planets and suns are stretched and ripped apart down to their very atoms and drawn towards the black hole.
So these jets that we've estimated have been going on for about 100 million years still have a huge amount of fuel available to them. That process can go on for an extremely long time, hundreds of millions of years.
Now, imagine taking a big chunk of that energy and releasing it in less than 2 seconds. That's what researchers believe happens in blast number 4, short gamma-ray bursts. Gamma-ray bursts are more concentrated than magnetar flares.
It's a concentrated beam of radiation, like a laser beam. It comes out as a narrow stream.
The gamma rays in the beams are also traveling much faster than the particles coming out of black hole jets.
The observations show that the energy is coming out in jets, moving at very close to the speed of light, 99.9999% the speed of light.
At that mind-bending speed, in just a few tenths of a second, short gamma-ray bursts can release as much energy as our sun does in millions of years. But for years, scientists couldn't figure out why some gamma-ray bursts were long, lasting many seconds or even minutes, while others were usually only a fraction of a second. Then, one burst in 2005 led researchers to an exciting new theory about incredibly dense neutron stars annihilating each other. The power of man-made atomic bombs is nothing compared to the galaxy-rattling explosions in the cosmos. as we continue counting down 10 of the biggest blasts in the universe. These cataclysmic events are now producing as much energy as our sun does in millions of years. Short gamma ray bursts are number 4. For years, scientists have been confident of the source of long gamma ray bursts, those that last over 2 seconds and sometimes erupt for many minutes. They come from galaxies with massive stars. And when certain massive stars die, they collapse and then explode, blasting out incredible amounts of energy as concentrated jets of gamma rays. But in 2005, detectors in space captured a powerful gamma ray burst that only lasted for a fraction of a second.
This was very exciting because all the gamma ray bursts we'd seen before were of the different variety, longer, coming from galaxies where massive stars were dying. This was something different. It was short, and it came from a region where no massive stars existed.
This burst came from a galaxy thought to have some incredibly dense neutron stars in binary pairs that orbit each other. And scientists believe that the only way to generate such a quick and powerful burst of gamma rays is if 2 neutron stars engage in a deadly dance, orbiting closer and closer, then finally crashing into each other. This is thought to be the moment when a black hole is born.
When the 2 neutron stars finally touch, one of the neutron stars gets shredded into a disk, and the thing that's left is too big to be a neutron star. There's no force in the universe that can hold up 2 neutron stars, so it collapses to a black hole.
The 2005 event, known as GRB 050509b, since it was the second burst to occur on May 9th of that year, was the first short gamma ray burst whose location was pinned down. It didn't look very bright from Earth, but that's because it was an astounding 2.2 billion light years away.
GRB 0509b lasted only about 40 milliseconds, but in that time, it released about as much energy as the sun will release in 100 million years.
But the power of colliding stars can't compete with the even larger amount of energy released when an entire star explodes from the inside out. Number 3, supernovas. When large stars die, they don't just fizzle out like our sun eventually will. They go out with a bang. There are actually several types, but the 2 main ways a supernova explosion happens is either when one star in a binary star system swallows part or all of its companion, or when a supermassive star collapses in on itself and ejects its outer shell in the process. Either way, a mind-boggling amount of energy is quickly released.
The energy of motion, the kinetic energy of the ejected material, can equal the total amount of energy that the sun will release over its entire 10 billion year lifetime.
The binary star type of supernova is similar to a hydrogen bomb, where runaway nuclear fusion leads to a massive explosion. These are known as Type 1a supernovas, and in 2003, one of these blasts flooded the cosmos with more light than an entire galaxy of stars combined.
It was over 20 billion times more luminous than the sun for about 2 weeks, and this all came from the explosion of something not much bigger than the moon, about 1.4 times the mass of the sun, from a thermonuclear explosion from fusion.
For the core collapse type of supernova, an incredible amount of power is generated when the outer shell slams down and gets an extra kick from the denser core of the star.
Imagine this ping pong ball represents that outer, lighter material of the star, whereas this superball represents the heavy inner core. You can see that the ping pong ball actually doesn't really bounce that much on its own. And there's the bounce of the superball. But what you'll see is that when I send them down together, the bounce of the superball back up will propel the ping pong ball much higher. And that's very much like what happens in the supernova, where you have the heavy inner core bouncing back out and meeting that lighter material and blowing it out.
In fact, one supernova explosion in 2005, known as SN 2005 AP, flashed brighter than all of the others for weeks on end. But it didn't do any damage to Earth because, luckily, it was also 4.7 billion light-years away. And like many of the other blasts on the top 10 list, supernovas don't just destroy.
A supernova is a little bit like a recycling center. There's a lot of material in those massive stars. It's anything from 8 times to over 100 times the mass of our sun. So there's a lot of material that's going to be processed in those stars, just like there's a lot of raw material here at the recycling center that's going to be processed.
The matter in the universe is dominated by light elements like hydrogen and helium. But the inside of a star about to go supernova is the main source of the various metals and other heavy elements we depend on for life.
Just like these materials are being sorted into different categories, the star starts to process heavier and heavier elements, starting with hydrogen, then helium, making heavier and heavier elements all the way up to iron when the fusion process stops. Later on in its life, when it becomes supernova, with the aid of the compression effects in the supernova, the star will make even heavier elements. Just as these materials are now packaged and processed and ready to leave the recycling center and go out into the world to be reused, the materials that were made in those stars that were then finally cooked and blown out into the universe by the supernova process, those will be reused as well. They may be used in other stars or perhaps other planets. The materials that we're made of here on Earth, the materials even in our bodies, those heavy elements were made in supernovae.
While supernovas are massive explosions themselves, they can also trigger secondary blasts with even more concentrated energy. Number 2, long gamma-ray bursts. The long gamma-ray burst comes out of the most powerful supernova explosions. They're as strong as the short gamma-ray bursts, but since they last much longer, anywhere from 2 seconds to nearly half an hour, they blast out much more energy overall.
The long gamma-ray bursts are completely different beasts compared to the short gamma-ray bursts. They're immensely more powerful, maybe up to around 10,000 times more powerful than the short duration bursts.
These concentrated jets of energy only come from supernova explosions involving stars 30 or more times the mass of our sun. And just like the short gamma-ray bursts, they're evidence of the birth of a black hole.
Long gamma-ray bursts are, in some sense, a variety of hyperenergetic supernova. The iron core collapses as before to a neutron star, but too much material falls down on it and it can't stay a neutron star. The temperature rises to 10 billion degrees. The luminosity in 1 cubic inch of this is as big as the sun. And this power can't flow out on the equator. It gets focused like in a shotgun blast out the rotational axis of the star.
So how much energy do the most powerful long gamma-ray bursts release compared to our sun? The answer is shocking. We're at number 2. in our countdown of the biggest blasts in the universe, long gamma-ray bursts. They're the most powerful concentrated beams of energy in the universe. They release many times more energy in a matter of seconds or minutes than our sun will produce in its entire 10 billion year lifespan. The key to their devastating power is focusing that energy in a narrow area. A firearms expert illustrates the point with two different shotguns. First, a shorter gun, where the shot spreads out quickly after leaving the barrel, unlike a gamma-ray burst.
As you can see, there's some damage to the melon, but not that much because the shot was spread out and only some of it hit the target.
Now our firearms expert is switching to a longer barrel that keeps the shot concentrated in a tighter pattern as it goes downrange. The same effect as a gamma-ray burst.
Concentrating the shot can be devastating. It's a good thing for us that most gamma-ray bursts are millions or billions of light years away from Earth and are pointed in the other direction.
It's believed that these concentrated jets shoot out when massive stars collapse into black holes. And in 2008, scientists detected one of the strongest gamma-ray bursts on record, known as GRB 080916C. It lasted an incredible 23 minutes.
This GRB was one of the most exciting blasts ever seen because the total power inferred from the observed brightness and the distance of the blast exceeded that of any other known GRB up to that time. Moreover, we can tell that energetic particles were blasted out along two jets at 99.9999% of the speed of light. GRBs are so powerful along the beam of particles and radiation that even ones that are thousands of light years away but pointing at us could destroy much of the life on Earth.
But if long gamma-ray bursts are the most powerful explosions in the universe, then how could they be number 2 on our list? Because the top spot goes to something that didn't happen within the universe, but happened when the universe itself was formed. Number 1, the Big Bang. This mother of all blasts is technically an expansion and not an explosion, since it was not a blast within a defined area.
It wasn't an explosion that happened somewhere in space. It's all of space. It's the actual fabric of space-time itself coming into existence. So in the concept of a biggest blast, it's as big as it gets. It was the whole universe blasting into existence.
And the speed and temperatures of the Big Bang dwarf anything that happened inside the universe once it was formed.
Those temperatures are beyond anything we can imagine. There are trillions of degrees if you measured it in usual units. So compared to any explosion, say here on Earth or a star or what have you, this is well beyond that.
Researchers believe that theoretically, they can go back so close to the moment the Big Bang happened that a fraction of a second doesn't come anywhere close to doing the timescale justice.
The bang of the Big Bang is a time in the early universe known as inflation. The size of the universe went whoosh. It just expanded so quickly, doubled in size many times over a very, very short interval of time. This incredible inflationary exponential state of expansion lasted only a tiny fraction of a second. a millionth of 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 a second.
During this early expansion, it seemed as if things were moving faster than Einstein's universal speed limit, the speed of light.
In fact, it expanded so quickly that it was faster than the speed of light. That's okay. That doesn't violate Einstein's theory of relativity. Space itself can expand faster than the speed of light. No particle can travel through space faster than the speed of light, but space itself can and does expand faster than the speed of light.
And the Big Bang is the largest reminder of all that the biggest blasts in the universe, these sudden releases of energy, do much more than destroy.
The creation of our universe, the creation of the sunshine that comes out of stars, and the creation of our own moon all came from this tremendous liberation of energy all at once. So there's a very intimate link between matter manifested in one way and then being destroyed and then re-emerging in a new way. And, you know, here on Earth, it re-emerged as us.
And as the universe evolves, its biggest blasts will continue to be both the destroyer of worlds and the creators of new possibilities.